Welcome learners to this new lecture series on electronic devices and circuit theory. This is your instructor Dr. Waleed Tariq Sethi. Have you ever wondered how these electronic devices that surround us communicate? If you have wondered about devices like diodes, transistors and their circuit combination, you have come to the right place. In this lecture series, we are going to look into these basic electronic devices and how they communicate, how they operate with each other, and what happens if we bring them together in a form of a circuit and then later on convert it into a network. For this lecture series, we will be utilizing a well-renowned book by authors Robert Boylstead and Louis Nashelsky. For the problem solving and analysis of various components, we'll be looking into the 11th edition of this book, and we'll try to understand the complex topics in the simplified manner so that you know how these components are working at the atomic level and what happens if they are combined into a network. So for this lecture series and from this main textbook, we'll be covering the first 7 chapters or the topics included in these first 7 chapters. We'll first start by understanding what are semiconductor materials and what are its basic elements at the atomic level. Then we'll look to the first basic semiconductor device, and that is known as a diode. What is its structure, its operations, its working principles and its applications. So if you have never seen a diode and just heard about it, this is how a diode or some of the diodes look like, which we normally will see in this course. We'll see its data sheet and we'll also see what happens in the laboratory experimentations. Moving on from the first semiconductor device, we'll move to a well-known electronic device in today's era, and that is a transistor. So there are various kinds of transistors, but our focus will be on two. The first is called a BJT or a bipolar junction transistor. Again, we are going to look its structure, working principle and various configurations. By configurations, we are going to see how the circuit gets excited if we supply a DC source and then we apply an AC source or an AC signal to this transistor. Following this transistor, we look into a second category of transistors known as field effect transistors. Again, we look into various biasing configurations and its excitation or supply in terms of DC and AC sources. Then finally, we'll conclude this lecture series discussing on the small scale signal or equivalent circuit models for both the transistors, that is BJT, and the field effect transistors. In front of you, there are various components that we are going to study in this course, starting with diodes. Then we are going to look into transistors, BJTs and FETs. Obviously, the main circuit elements, which is the resistors, the capacitors and the inductors, are going to play a crucial role in the circuit analysis of these electronic devices. We'll also look into the measuring tools like a digital multimeter, and then various motors and Zener diodes and LEDs will be also looked into it. So this is a picture showing all the components or the electronic components that are of interest to us for this lecture series. So now let us dive in and begin understanding electronic devices and components. We first start with the first chapter from the main textbook, that is talking about semiconductor devices, materials, and then we'll move to the semiconductor diodes. Before we begin, I request that you subscribe the channel and hit the bell icon button to get regular updates on the channel and various topics related to electronic devices and circuits. So in the first chapter, we are going to cover these contents, or the objectives of the chapter are such. We are going to first understand what are the materials that makes up any electronic device. This is the naturally occurring materials like silicon, germanium and gallium arsenide. Then we are going to look into the atomic level and see how the electrons or holes move about and how they are getting attracted and repelled off of each other. After that, we are going to look at the bigger picture and see what are n-type and p-type materials. Then we are going to talk about the first electronic device, that is diode, and what is the method to excite the diode. When no voltage is applied, we call it as a no biasing. What happens if a forward bias or a reverse bias is applied, and what are the regions associated with the diode. Then we are going to see what are the various resistance levels with the diode, and then we are going to see the equivalent model or equivalent representation of a diode. And finally, the chapter concludes by giving an introductory description on the Zener diodes, which are the special kinds of diodes, and how the LEDs work. So these are the 7 objectives that we are going to cover in this lecture series from the first chapter. So let us begin with the first important concept, and the question arises that what is electronics, what are devices, how do we compare an electric circuit with an electronic circuit. So if we talk about its definition, electronics is that part of engineering that normally uses electricity, and the main purpose of this is to control the flow of electrons or to have communication with other devices or circuits. So we can simply put it in this way, that electronics deals with the flow of electrons. So if we have certain electrons and they are flowing, so how can we basically control this flow of electrons? So the main keyword over here is controlling the flow of electrons. So how do we differentiate this with an electric circuit? So when we talk about electricity in electronics, we are talking about the flow of charges, and in our case this translates into a current. So when we are talking about electronics, we want to basically control the movement of charges, or in another way we want to control the flow of current. So how can we differentiate an electric circuit with an electronic circuit? So at a very basic level, let us say if I have a voltage source, and if I have a resistor, and I have a load in the form of an electric bulb, and this is a voltage source, we have a certain resistor, and this is the load, which is an electric bulb over here. So if I talk in terms of an electric circuit, this is an electric circuit. Now what happens in the electric circuit is that this volt is going to generate a current, and the current is going to be such that it is going to pass this resistor, and then the bulb will start to glow, given we have enough voltage that generates this current. So this flow of current in this dedicated path is an electric circuit. Now how come we define the electronics for the same circuit? So in electronics, we want to control the flow of electrons. So what is going to happen is that the same voltage source is basically going to generate the current. The current is going to move, it is going to pass the resistor, and now it is going to come to the bulb. The same bulb is going to glow, but since we want to control the flow of electron, you might have seen in your houses we attach a dimmer switch to it. So this is a dimmer or a switch where we can control how much bright or how much light we want to increase the intensity of the bulb. So if we want to control the glow of bulb, that how high it glows, or should we reduce the intensity of the light, so this is where we are controlling the flow of electrons. So we can say that in electronics, the flow of electrons gives us the flow of current, and in electric circuit we are unable to control the flow of current because there is a dedicated path where the current flows and performs a certain task. In this case, it glows a bulb. Yes, there might come a question that what are switches and relays? So they are also a form of controlling the flow of current, but they give you a positive or a negative response. For example, if I add a switch over here and we are considering an electric circuit, that switch, if is open, will not allow the current to pass. But if the switch is closed, the current will easily pass and go towards the load, and this load being our bulb. But if we want to increase its intensity, we have to control it with a device, and thus the electronics comes into play. So all in all, the difference between electric and electronics is that in electric circuit we have a dedicated path and we perform a certain task. When it comes to electronics, we perform the same path, same function through the dedicated path, but here we are able to control the flow of electrons, which means we can control the flow of current. And again, the control is done specifically to perform a defined task. So perform a defined task. So this is a comparison between electronics and an electric circuit. Now if we talk about electrical and electronics in a broader perspective, there is another comparison, and that is shown in the images onto your left and right. So if we talk about the electrical perspective, normally electrical circuits basically deal with the generation, transmission, distribution and consumption of energy. So this is basically related to very high voltages. For example, if you have a electric power grid, so basically this is dealing with voltages that are in kilowatts, and these are very high voltages. But when we talk about electronics, again we are dealing with the generation and transmission of the electrical signals, but this time the voltages are very low. Normally we stick to plus minus 5 volts, and sometimes we can go to 15 volts if you are performing certain lab experiments with your trainers, but the voltages are very low. And the advantage of this is that we have the circuit components that are easily dealt with these low voltages, and the experimentations can be easily performed. So another difference between an electrical and electronic circuit is the context in which it is utilized. When we talk about electric circuits, we are dealing with very high voltages, and when we talk about electronic circuits, for example, your gadgets, your cell phones, your laptops, the voltage inside is very low, ranging from 5 to a maximum of 15 volts. So this is the comparison between an electric circuit and electronic circuit. We have seen that electric circuit follows a dedicated path, or the current follows a dedicated path. In electronics, the current also follows a dedicated path, but we can control its flow to perform a specified task. For example, in this case, controlling the intensity of the glow of bulb. Now, another thing is also necessary when dealing with electronic components, and that we are going to see in the coming slide, is with which this electronic component is made, and that is associated with the material of the device. So what about the material? We'll look into this. So this is the second important thing that differentiates our electric component compared to an electronic component. So let us see what else we know. Now let us talk about the various levels of these electronic devices. Obviously, the first is at the component level. The component level means that the capacitors, the inductors or the diodes specifically. So the symbol of diode is this, and the transistors, if we are talking about a BJT, it is going to be something like this. We are going to look into these symbols, don't worry. So the thing that I talked about is how are electronic devices made, or from which material it is made. So at the component level, we basically have various components that are made from a special material that defines that component to be an electronic component and not an electric component. When we talk about an electric component, we say these are the basic elements in RLC, which is resistor, inductor and capacitor. They are made from the known materials like copper. You sometimes have aluminum. If you have more premium elements, it can go towards silver as well. Sometimes for gold and silver as well. So the symbol for silver is Ag and gold is for Au. But when we talk about the components or the electronic components, we don't use copper, silver, gold or aluminum. Rather, we use another component, and we are going to see what is that. So this is the electronic components as the basic level. Now in the second stage, when we combine these components together made from a special material, we say that we have formed a circuit. So a group of components brought together to perform certain controlling operations, we say we have formed a circuit. And here you can see a circuit that has been formed, where we have a voltage source applied, we have a capacitor, we have a diode placed in this orientation, another diode followed by this in the different orientation, and then you have diode 3 and diode 4, and this is basically a group of diodes arranged or oriented in such a way to perform a certain operation. So we say that the second level of electronics is the circuits. The first level are the individual components made from a certain material. When we use those components and combine them together, we move to the second element, and which is known as the circuit. And finally, the third process in the evolution of electronics is how we group them together and present it in an electronic device. Obviously, these are those things that are available to us in the market. And so you can see the cellular phones, you have your laptops, you have your LCDs, you have your systems, you have your monitors. So this is the front end of the system, where the user just sees the aesthetics of the device, and it is not aware what is happening at inside the device, which is at the first and the second level. Since we are electrical and electronic engineers, we are mostly interested in the first and the second level of electronics. The third is something which is associated with the hardware side, or the assembling of the devices, or the aesthetics of the devices. So in this course we'll mostly stick to the first and the second level of electronics, that is the understanding the component level of electronics and what happens if we make a circuit out of those components. So now let us look at the material that I have been focusing on, that what kind of material governs that this device is an electronic device and this is an electrical device. So obviously our goal in electronics is to control the flow of electron to perform a certain task. By controlling the flow of electron, we are basically controlling the flow of current. So in nature there are three materials, or normally when we are talking in terms of engineering or materials engineering to be specific, we talk about three elements that are used to make those material devices. The first is a well-known, which is known as a conductor. So the property of conductor is that it allows easily the current to pass, and we say that it has low resistance. The value of R is almost negligible, or sometimes we associate certain values like 10 ohms to 1 mega ohm, depending what is the need for that resistor. If we are just using it as a safety portion, then we can increase the value of resistance. If we are just using it to pass the current or a controlled amount of current, then we talk about it in the values of ohms. The second element where we utilize mostly is not a conductor, rather it is called an insulator. Again, the properties of insulator is that it has a very high resistance. So the value of R is very high. Sometimes it can go toward infinity. So this is a material where the flow of current is not possible, or it becomes very difficult. So these kinds of devices are known as insulators. But the device, the material that is in interest of to us in this course is a semiconductor device, and this is the building block for any electronic material. So semiconductor devices are those that allow the current to pass, or sometimes it blocks the current. So you can understand that semiconductors are something which is in between conductors and insulators. So this is basically a semiconductor device, and those materials or those devices or those components which are made from a semiconductor material are termed as an electronic device. So now let us look at the atomic level and see the comparison between a conductor, an insulator and a semiconductor. So in this comparison chart, the first column is talking about the materials and the properties associated with conductors. The second is about semiconductors, and the last one is about insulators. So we have seen that conductors are the materials that basically allow the current to, or the charges to pass through them. Obviously it is affected by heat as well. So what happens at the atomic level? So here we can see what is happening at the atomic level when we are talking about conductors, especially the flow of electrons within a conductor. So here you see atomic structure. Atom is the smallest particle of matter. We are going to look what are the attributes of an atom from the Bohr's model. But what normally atom contains is a nucleus. So this is the nucleus, and it has a neutral atom, and then this is an orbit, and these black dots are basically your electrons that are moving. So you can see that if this rectangular box is any material, let us say it's a copper material, so I call it as a copper. Now what is happening at the atomic level, that the electrons are easily movable from one atom to the other atom, and you can see the movement in terms of these black dots. So these black moving dots are the electrons that can easily move from one orbit to the other orbit, and there is least resistance offered by the material. So this is how conductors work, and that's why we say conductors have high conductivity, and the forbidden gap is very low. The forbidden gap is basically the gap between these two elements, and the electron can jump from the valence band to the conduction band. We are going to look into the energy levels as well. Obviously other parameter is that it has low resistivity, temperature is positive, coefficient is positive, like when we apply the temperature, the electrons can get excited quickly and they can move. The best examples of these materials are gold, bronze, silver, copper and brass are widely used in our electronic or electric devices. Normally you have resistors made up of these coppers, You have inductors and capacitors are also made from this, and this is basically utilized in any electric circuit or an electric component. So this is the table or the column talking about the characteristics of conductors. So before moving into semiconductors, let us look at insulators first. So this is an insulator. Again, this rectangular box represents any insulating material. For example, it can be wood, paper, rubber, any wall. So this is an insulator. Now what is happening at the atomic level? You can see the electrons are just orbiting around their shell or their orbits. So they are just revolving around their orbit. They are not able to jump from one orbit to the other orbit. This is not allowed insulator because the gap is too much. The forbidden gap is so high that the electrons are unable to move from one orbit to the other orbit. In order for them to move, you need a very high amount of energy, and that requires more power supply. So normally in insulators, the energy band gap is very high, and the electrons at the atomic level are unable to jump from one orbit to the other orbit, and thus the current has difficulty moving within the insulating materials. And finally, we talk about the third material, and that is insulator. So insulator is the material which is normally we talk about the semiconductor material, and this is the building block of the electronic components. Now what is happening in the semiconductor material? So in our case, the best semiconductor material that we are going to use is made up of silicon, and this is a rare earth metal that is available to us on earth. So the property of semiconductor material is that it can be converted into a conductor if a proper amount of energy is supplied, or it can also be converted into an insulator if that point of energy is removed. So in ideal state, if no energy is given to a semiconductor material, for example a silicon, in ideal state it will act as an insulator, and the moment you provide an energy to it in the form of temperature or an external energy, that energy can come from a voltage source, or it can be from a light source. So that energy excites these electrons that are in this stationary mode, and thus they become free electrons. Once they become free, they are able to conduct. So semiconductors in their pure form act as an insulator, and if you want it to become a conductor, you can provide an external energy, and thus this is the way we are controlling the semiconductor material, and thus it comes back to our basic definition of electronics, that electronics deals with the control of flow of electrons to perform certain tasks. And that's why most of the electronic devices or components are made from semiconductor material. The first and the foremost and the abundantly used material is silicon. This is aluminum is not used. The second material or before silicon is germanium, and sometimes we use a combination of materials like gallium arsenide. So these are the three widely used devices as semiconductor materials, and we are going to look into these devices shortly. So this chart over here shows a comparison of the three devices that are likely to be used. If you are working with electric circuits, you have conductors. If you are working with electronic components, we use semiconductor materials. So before we proceed, let us look to history and see how we have, or how the electronic devices have progressed so far. So before the invent of these semiconductor materials like silicon and germanium in the early ages, our electronic devices or the operations performed by these electronic devices like the flow of electrons was done through known device like vacuum tube, developed in 1905 by Fleming. You might have heard about these devices in your junior levels or physics classes. So the vacuum tube was such that it was basically performing various operations. So the working principle of vacuum tube, without going into further details, is it is a structure made up of a glass. So you can see its shape over here. The normal size may vary from 1 to 6 feet. So this was a huge device, and at one end it had anode, a positive terminal. The other hand had a cathode, a negative terminal. and sometimes this cathode was a heated rod, so normally it got heated. Inside there was nothing available, so we created a vacuum, and thus the name came as vacuum tubes. What happened is when we excited this cathode, it got heated up, the electrons started to flow from the negative side, and they started to move in the upward direction in a very fast way towards the anode, and thus this circuit was completed and we got the flow of charges. Sometimes an inert gas was also introduced inside this vacuum tube, so it was not completely a vacuum. And you can see the example of this inert gas in your homes in the form of tube lights. So this is a best example if you want to see what a vacuum tube with an inert gas looks like. So the tube lights in your house or homes are basically a vacuum tube, but it has an inert gas inside, which is normally an argon or a krypton, and thus the molecules interact with that gas, creating a UV light, and then you are able to see the white glow from your tube light. So this is what an inert gas introduced inside a tube, but most of the cases there was no gas and it was called a vacuum tube. Now the problem associated with this is that the size of these tubes were huge, and it took a lot of time for the charges to move from cathode towards anode. But later on, when the electronic devices, especially transistor, was discovered, you can see that the technology boomed and the size of the component reduced. The best example is your Intel IC chips, that a normal chip in your computers contains around 731 million transistors, and the space is just 1.67 square inches, so it's very small. The devices have reduced, and we have covered a long way, starting from 1910s to 1920s and 1958, and when the devices were discovered, especially the silicon and germanium, in 1947 and around 1960, the vacuum tubes became obsolete, and then we moved from vacuum tubes to something known as today as solid state device, or you might have heard its short form as SSDs. So these are the hard disks in your computers, in your laptops, which we are calling as solid state devices, because now instead of using vacuum tubes, we have small transistors such that the electron can flow very easily. For example, if we talk about a solid state device like a transistor, so now you can see these are the paths for the electrons to move. So it can easily move from, let's say, collector, we have a base, and then we have an emitter, and this is an NPN. So the current can easily move between this path in a fastest way compared to a vacuum tube, where the electrons will take a lot of time in the gaseous form to move from cathode towards anode. So this is the solid state devices. Obviously, the evolution was not easy. There were limiting factors, but we overcome those factors. And what were those limiting factors? So these were the 4 limiting factors or major factors that limit the evolution of these devices, and still they are challenging, but most of them have been overcome. The first was the quality of the semiconductor material. So as I mentioned, the elements that we utilized, the first element that was available was germanium, and we will see that the problem with germanium was something that we shifted from germanium to silicon, and now the thing is that we have to figure out how to create a purest form or purest crystalline of this silicon. So this is the first hurdle that we face, but nowadays the technology is such that we are able to generate a pure silicon crystal. The second was the design technique, that how we can basically shape these elements. So this was the limitation. And the third was the manufacturing equipment. Obviously, if you want to reduce the size or the thickness of material, you need to have a nanofabrication. So in those days, in 1980s, 1950s and 1960s, nanofabrication was not possible. Nowadays we have this facility and we have those gadgets in smaller sizes. And finally, limitation is an innovative idea, and still it is challenging for today, that how can we assemble these components together in a small package, thus that there is no loss of signal or no loss or no heat involved in the components. The best example in the year 2025 that we have seen is, you might have heard about NVIDIA's processing unit called Digit. So this device has just been announced in the year 2025 at the Mobile Week Congress, where NVIDIA has launched this device. You can see the size of this device. This is a simple processing unit. So nowadays, even if you compare it with your keyboard, the size is small. It is like in 96 into 205 into if I'm not wrong, 10 millimeters. So this is how small the device is. So if you compare it with your traditional PCs at home, the technology has reduced so much that your whole PC or processing unit comes with this dimension compared to what we had vacuum tubes which were 1 to 6 feet tall. So this is how the technology has evolved, and we have basically dealt with most of the limitation factors, but still we are trying to cover all the factors. You might know that nowadays the technology or the nanochip in your cell phones have reduced from 9 nanometer in thickness to 3 nanometer, and still we are trying to bring it down to 1 nanometer. So this is how the technology has moved from past technologies to the future, and the future is obviously reduction in size with more components compressed together, like what we see in this NVIDIA's digit box, and you might have seen this in Apple's mini PC as well. So the size has reduced a lot. Again, to give you some perspective in terms of vacuum tubes and solid state devices, you might have seen in your old TVs, if at home nowadays, I think they are obsolete, but this is how a vacuum tube looked like. You had an electronic gun, and then you had this screen where the gas was used to pump electrons from one point to other points, and then the picture was displayed over here. Nowadays the old vacuum tubes have been replaced by LEDs panels, so you can see all these LEDs have millions of transistors and electronic devices like diodes over here. Similarly, you can see a new company has come called Carry Audio, which are trying to create those nostalgic devices. So this is a comparison of an AM FM radio receiver. This is a digital receiver. It can receive your AM and FM signals, and just to put into context, they are trying to propose their old age devices made up of vacuum tubes. So these are various vacuum tubes. Again, they have tried to create this nostalgic device, but again it is not compact compared to a digital FM. The transistors have to be placed on top of it, or the vacuum tubes based transistors are placed over here. But this is a picture just to show you the comparison between old devices and the new technologies that have reduced in size and increased in performance. So now let us come to the second important element which I talked earlier, which defines an electronic device, and that is the semiconductor material. So we have seen what is a semiconductor, that lies between conductor and insulator. So now what are the semiconductor materials that we utilize to make these devices? So this is a picture of a semiconductor material that is found in rare earth metal. So you can see it's kind of a piece of rock, but it is silver in color. So mostly the materials are existing in nature. So we take these materials and we construct our solid state devices. So these devices gives us the property that it can behave as a conductor, or it can also behave as an insulator. So as I mentioned, if the semiconductor is in its pure form, so if the semiconductor is in its pure form, let's say if the material is silicon, it normally acts as an insulator. But if we provide some external force, it becomes a conductor. Again, we can control that how much conduction we want from the external excitation. So in nature, semiconductors which are found are divided in the fabrication process into two ways. We can consider them to be a single crystal, and thus we can say that we have a single crystal of silicon and germanium. And if you want to have the properties of both of these devices, you can make a compound of this structure where we have these three elements that are widely used. This is gallium arsenide, cadmium sulfide, and gallium nitrate. So these combinations basically gives us more control in terms of processing power, or normally we said that the speed of communication is normally increased when we used combination or compound semiconductors. But most of the devices or single elements like diodes, transistors, either BJTs or FOTs, are made with single crystal elements. So this is basically two types of semiconductors that we extract from nature, and then we mold them or fabricate them in our industries. Now let us look at the evolution or moving from germanium element to silicon, and nowadays why silicon is abundantly used. So in front of you, you can see that the diode discovery happened in 1939, and later on transistor was discovered, which was an extension of the diode by adding a third terminal. But during that time, these elements were mostly made from germanium. And why? Because germanium was widely or abundantly available, and the processing of creating a pure germanium was easily done. But the problem associated with germanium was that it was temperature sensitive. So if the temperature got increased, your devices will overheat. On to your right, you can see the chemical characteristics of germanium, and we can see its atomic number is 32, its symbol is Ge, its weight is 72.61, and this is the chemical configuration of this electron. So don't worry, we are not going into the chemical aspect of it. The only thing needed for us is that we should know the symbol of the semiconductor material and its atomic number. Then in 1954, the first silicon transistor was introduced. So the researcher or scientists already knew that silicon existed. It was better in terms of temperature sensitivity, but the problem was that there was no machinery available to make it as pure or to mold it into different devices. Once the tools were available, then in 1954 we moved from germanium to silicon, and nowadays most of your components are made from silicon wafer. Most of the ICs and devices are silicon based. Again, onto your right, you can see the symbol of silicon and its atomic number, which is 14. Then in the 1970s, when the computer processing was gaining interest, the scientists found a way to increase the processing power or communication between different ICs or chips. And for that case, they made use of two different semiconductor materials and joined them together, and thus we got gallium arsenide, which gave good its speed in terms of communication between electronic components, although the cost would increase if you are using compound elements. Again, gallium has symbol Ga, atomic number 31, and arsenic has symbol As with atomic number 33, but this is a compound structure, so it is basically utilized together. It comes as a single element, but both of them are added together. And in most of the devices nowadays, if you want some device that has fast processing speed, you will have the compound silicon or semiconductor material inside of it. So since we are talking about the chemical properties, we need to know about the atomic structure or what is an atom. So you might have heard about atom in your lower levels education institutes. It is a property of matter. And what is matter? Matter is basically of different sizes. So everything in this world, we say that physically it is a matter, and it will have at the atomic level different charges. So the properties of matter, it can be either solid, for example a desk, a pen, wood. So this is a solid device. Another property of matter is liquid, water, gels, solutions. This is a property. The third matter is the gaseous form, for example methane, chlorine, fumes, carbon dioxide. So these are properties of matter. And the fourth property of matter is called plasma. So the thunder strikes that you see, this is plasma. Basically, if you have a gas and you excite it with a voltage or supply and electricity, you will get a plasma. So these are the four properties of matter, and atom is a part of this matter. So what is inside a matter? So you have a nucleus shown over here that has protons and neutrons. You have these shells, which are called shells or orbits, and on these shells you have electrons represented by these blue dots. So each shell has a specific number of electrons associated with this. Now, how do we come to know about these electrons and these shells? So obviously there are theories by various scientists, but the most prominent one is the Bohr's atomic model. And Bohr has given us different postulates that defines an atom, where we have a nucleus surrounded by orbits, and he has termed those orbits as digits like orbit 1, 2, 3, 4, or you can identify them as levels like K shell, L shell, M shell, and N shell. And on these levels there are different number of electrons, which are called stable electrons. So just to give you a recap of Bohr's atomic model, so the postulates of Bohr atomic model is, so I'll try to write them over here. The first postulate is that the electrons over here, so consider that in these shells these are electrons, randomly placed. So obviously there is an order of these electrons. It's the power of 2 power n. So one shell can have 2 electrons, then you can have 4, then you can have 8 electrons, and so on and so forth. And this comes to the postulates of Bohr's model. So the first postulate of Bohr model is that electrons move around the nucleus in fixed circular paths. Around the nucleus in fixed circular paths. So this is the first postulate given by Bohr. Again, this is the orbit and electrons are moving, let's say, in the clockwise direction. So this is the first postulate given by the Bohr's atomic model. The second postulate which Bohr gave us based on his understanding of the atomic model is that the force that binds the electrons to the nucleus, so the binding force of electrons with the nucleus is given by the Coulomb's equation or force of law equation, F is equal to K Q1 Q2 divided by R square. So this is the Coulomb's equation where Q1 and Q2 are the charges, K is the constant, and R square is the distance between these electrons with regards to the nucleus. So this is the force that keeps the electrons binded to the nucleus. If the electron is closest to the nucleus, it has more force and more energy. If the electron is far, it has less energy compared to the nucleus, but it has more force, so that it has jumped from the nearest shell to the outer shell. The third postulate that Bohr gave us, that the orbit of electron does not change unless it is acted upon by certain force. So we can say this, that electron moves between shells or orbits, let's put it in a simple way, when external force is given. External force is applied, or electron loses the energy it has. So this is what it means. So the electron, if it, for example, if I have this electron and if it jumps from this green lower orbit to the blue orbit, it has gained energy. So this is what it means, that the electron is not it is only going to change its orbit when it's gaining energy. Similarly, if this electron was at the high level and it loses its energy in the form of radiation, it will come back to the lower level. So this is what it means by electrons' behavior inside the orbit. The fourth postulate was that the movement of electron between the electrons movement between levels between the shells or orbits, from higher orbit to lower orbit or vice versa, is basically represented by a mathematical expression, and that is delta E equals to hc by lambda. So this is the energy of the electron present inside, and this is given by the Planck's constant, where h is the Planck's constant, lambda is the wavelength, and c is the speed of light. So the value of Planck's constant is 6.62 into 10 raised to power minus 34 joule second, not per second, it's joule second. So this is the constant, the Planck's constant, and thus we can find how much energy the electron has released from this equation. And finally, the movement or angular momentum of electron, angular momentum of electron. So the way the electron is moving in this shell is quantized, meaning it has a certain value. It is given a specific value, and that is by the equation mvr is equal to nh divided by 2 pi. Basically, mvr is normally also represented by alphabet L. So the equation is nh divided by 2 pi. So this is basically a specific value or quantized number of value is given to the angular movement of electrons. By angular momentum movement, we means that how the electrons are moving about this orbit. So these are the 5 postulates given to us by Bohr, and from here we concluded that how the charges are moving inside the matter, or how the atomic model is behaving. So sticking to the atomic structure of silicon, germanium and gallium arsenide, again we don't want to go inside the periodic table and the chemical properties, we just want to utilize the information for our understanding. So there is a term called valence electrons. So if we take the example of silicon, we know the atomic number of silicon is 14 and the symbol is Si. So how these elements are distributed? So again Bohr said that each shell over here is basically going to have an energy, or the number of electrons in these shells are normally represented by a value of 2n square, which we are going to see shortly over here. So basically the maximum number of electrons in any shell according to Bohr's law is 2n square, which means if we talk about silicon and the 14 atomic number, how they are distributed in its orbit is such. So this is the nucleus. The first orbit is going to have 2 electrons, the second is going to have 8 electrons, 3, 4, 5, 6, 7, 8, and the last one is going to have 4 electrons. So in total we have 14 electrons in this complete atom of silicon. And now in these 14 electrons, our interest is with the valence electrons. So valence electrons are those electrons which are available at the outermost shell of the atom. So in this case we have 4 valence electrons, which is 1, 2, 3 and 4. So silicon has 4 valence shell or 4 valence electrons. Similarly, if you talk about germanium, 32 atoms are distributed over here in the complete orbits, and again it has valence electrons of 1, 2, 3 and 4. So it also has 4 electrons. What about gallium? Gallium has 31 and its valence electrons are 1, 2, 3. So it has 3 valence electrons. And similarly for arsenic, it has 5 valence electrons, 1, 2, 3, 4, 5 valence electrons. So this is of importance to us, that what are valence electrons. Now why these valence electrons are needed? So we are going to term these valence electrons as, for example, for silicon and germanium we are going to call them as tetravalent, for gallium it is trivalent, and for arsenic we have pentavalent. And we know that these are distributed because of the Bohr's law of 2n square. Now once we know about these valence electrons, we talk about something which is known as covalent bonding. You might have heard about this in your chemistry course as well. So now what is covalent bonding? So whenever we take a pure crystal, let's say if it is a germanium or silicon, we basically see that it forms a lattice structure. Now what is a lattice structure? So the lattice structure is basically formed because we combine the valence electrons of one silicon with the nearing by silicon, and thus combination of these creates a lattice. So you can see it over here. Let us say if I took one silicon atom, so I know that it has 4 valence electrons. So this is 1, 2, 3 and 4. Similarly in nature, if we bring it close to another silicon, it is also going to have 4 valence electrons. Now combination of these 2 valence electrons creates a bond which is known as covalent bonding, and thus if you keep on increasing this, you come up with something which is known as a crystal, or normally we call it as a crystal lattice. And this complete structure over here is a crystal lattice, and this is happening naturally when a pure silicon is formed or it is made. Now again, to put things into perspective, how the covalent bond is happening, let us say if I take one silicon and bring it closer to more silicon atoms. So what is going to happen? The covalent bonds, when they come in close vicinity, they are going to interact with each other. So you can see the covalent bonds are going to create what is called a combination of tetravalents, and thus a structure is born. You can think of this that if you bring 4 people together and they form this rectangle or this pyramid by joining hands together, so now the bond is strong. So this is known as covalent bonding, and normally in its current state, as I mentioned, silicon acts as an insulator. Now what happens is that whenever we apply an external force, we can break one of these electrons from its bond, and it will become a free electron, and it will start to move over here, and it can go anywhere. So this we are going to see. But now we are talking about covalent bonding, where all the atoms that are brought close to each other, their valence electrons, whether they are tetravalent, trivalent or pentavalent, they are going to create a bond, and thus a lattice structure shown over here is created. And this is how a purest silicon material is created. So other examples of covalent bonding other than the solid state is in metals and in gaseous forms. So if you have, let's say, a metal arsenic, it has 1, 2, 3, 4, 5 pentavalent or 5 valence electrons. If you brought it closer to a gallium, it has 3 electrons. So you can see the covalent bonding is formed between here, here, and here, and thus in natural formation, these metals create a covalent bonding. Similar structure goes for gaseous. If you bring two hydrogen atoms, they are going to form a bond, and thus you get a hydrogen or H2 molecule. If you have two oxygen atoms and one carbon atom, you get a CO2 atom over here. So the bonding is also happening in the gaseous state as well, in solid state as well. So this is covalent bonding. Again, remember, this is happening in their natural form, in their normal scenario. So now let us talk about the energy levels associated with these electrons. We already understood the equation. When the electron moves from one orbit to another orbit, its energy released or absorbed is given by the Planck's constant equation, which is delta E is equal to hc by lambda. So what else is observed in terms of material? So here the energy level basically is telling us how the electron is going to conduct when it moves from a valence to conduction band. So here we have a nucleus. This is one portion of the lower orbit, and this is the portion of the higher orbit. So we have just taken one quadrant of it. Now we talked about something known as an energy gap. So this is an energy gap. So what happens is, if the electron in the lower orbit attains a certain amount of energy, it is able to cross this energy gap and jump to the next nearing orbit. So we say that it has been moved from a valence band to a conduction band, in simple words, or the electron has gained certain energy, that it has jumped from the lower band to the higher band. So we call this that it has crossed its energy band, and it can also come back when it loses its energy. It can jump from the higher level and come back to the lower level. So this is also possible. So it's vice versa. So let us see what happens in terms of the materials like conductor, insulator, and semiconductor, and what is this energy level that is necessary to create this kind of a material. So if we talk about conductors, we see that this is the valence band and this is a conduction band. Valence band is something where the electron is currently in its normal state, and if it requires certain energy, this portion is the energy gap. So we start first with the conductor, and we have seen that in conductors, electrons can easily move from one orbit to the other orbit. So if you can see in conductors, the energy gap is very small. So if a small amount of energy is given to this electron, it will easily cross this energy gap and come to this orbit, where we say now it is ready for conduction. It has come from the valence band to the conduction band. If we talk about insulator, this is our valence band where the electron is in its energy or ideal state, and if it needs to come from the valence to the conduction band, it has to have energy of greater than 5 electron volts. If the energy is not greater than 5 electron volts, the electron will not be able to jump, and thus we say that insulating materials, the current cannot easily pass because it doesn't have enough or sufficient energy. Now what is 1 electron volt? So 1 electron volt is basically the charge of electron, which is 1.6 into 10 raised to power minus 19, and if you multiply it with 1 volt, so you get 1 electron volt of energy, or you can say it is 1.6 into 10 raised to power minus 19 joules. So this is the amount of energy. So in this case of 5 electron volts, you multiply it with by 5. So this much amount of energy is required by this electron to move from the valence band and come to the conduction band. In case of conductor, this energy is very less, so the value of Eg is almost very less, so the electron can easily jump a small value. But in insulator, it is very high, it is around 5 electron volts. And now what happens in semiconductor? In semiconductor, you can see that the energy or level or Eg is small compared to the conduction band, compared to the insulation band. So the valence electron, if it is given a small amount of energy, it can easily jump to the conduction band, and here we can see the amount of energy needed for all the elements. For example, if we have a material which is made from silicon, it will need an energy of 1.1 volts so that the electron can jump from the valence shell to the conduction band. If it is a germanium, it is needing 0.67, and if it's gallium arsenide, it's going to need 1.41. So since these energy levels are obtained easily, we can create a semiconductor material. And how this energy is given? So mathematically we know that work done on a charge is the charge per the voltage. So this is the energy equation. So W is our energy that is generated as per charge is getting applied by a certain voltage. So this is basically what is happening inside the insulator, conductor and semiconductor materials, that whenever we want to create a semiconductor material with silicon, germanium or gallium arsenide, the amount of energy Eg should be these standard values. In case of insulator, we need a very high amount of energy, and in conductors the Eg value is negligibly very small. So that's why the electrons can easily move from one point to the other point. So this is how the energy levels are working at the atomic level. Finally, we talk about something which is known as intrinsic and extrinsic semiconductor. So whenever we are talking about a pure semiconductor material, we say that it is an intrinsic material, which means that it hasn't been affected, its crystalline structure is pure, there is no impurity added. When we talk about impurity, we use the term doping. So doping is that if you introduce an impurity inside a pure semiconductor material so that you can control how many electrons will move from the valence to the conduction band, as we saw over here. So we basically are doping the materials. So when you don't dope, we say that it is a pure or an intrinsic semiconductor, and if you dope the material, then we say that you have created an intrinsic or extrinsic semiconductor. Obviously, inside the semiconductor, the properties of silicon mobility charges are given over here. So again, this is just for our information, we are not going to utilize this. Now what happens in intrinsic semiconductor? So this is an animation that shows how the crystal's lattice structure is formed. So in its purest form, when all the atoms are brought together, you can see the covalent bonding being created. Now what happens is that in this pure crystalline form, if you apply a certain force in the form of heat or light, you can see that one of the electron starts to move away from its covalent bond, and now we call this electron which is going to move as a free electron. This free electron can perform conduction, and we can say that the electron has moved from the valence shell to the conduction shell. So this animation will give you a clear idea how the intrinsic semiconductor can be made into an extrinsic if we provide a certain external force, or what we call as doping. Now in extrinsic semiconductor, we have two kinds of materials that are created. Since we are adding impurity or doping the pure semiconductor, we create two types of materials, which is known as N-type or P-type. Now an N-type material, it is also known as a pentavalent because it has 5 valence electrons inside the structure, and a P-type is known as trivalent because it has 3 valence electrons. So if we want to create a semiconductor material by doping, we can create two categories. The first is called the N-type and the second one is called P-type. Now let us look into these two types of extrinsic semiconductor materials. So what happens in the N-type material is that we dope it with a pentavalent atoms. So the best is to look at this example. So we have a crystal lattice structure of antimony with a symbol of Sb. Now what is happening over here? We took a silicon crystal lattice. So this is a silicon, 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 silicon. Now what is happening? Silicon has how many valence electrons? 4 valence electrons. So it is 1, 2, 3, 4. And we brought inside this structure an element from the outside, and we doped this silicon with an element called antimony, or symbol having Sb bismuth. And what the antimony has, it has 5 valence electrons. So this is 1, 2, 3, 4, and this is the 5th electron. Now what is going to happen in terms of covalent bonding? Silicon is going to covalent bond its 4 valence electrons with the bismuth's 4 valent electrons. So this is the covalent bonding between. What is going to happen is we will be left with one of the free electron over here. So this is the free electron of the bismuth, and this is now moving here and there. So this can be used to conduct, or it can be moved to any of the electrons. Whenever it finds the free space, it can become part of that. So this is how the doping is happening or this is how we are creating an n-type material. And you can see the negative or the electrons are in more quantity, so we are calling it as an n-type material. So again, to summarize, whenever we have a pure silicon, and if we bring another element from the outside that has more number of electrons than the valence electrons of the silicon, we say that we have created an n-type semiconductor, and this free electron is now able to move here and there, and it can be used for conduction element. In n-type material, the majority carriers are negative or electrons, and obviously the minority carriers will be holes. Similarly, if we talk about p-type material, if you want to create a p-type material, so what is again going to happen? We again have a pure silicon material or a lattice. It has its 4 valence electrons, and this time we have introduced an external element, or we have doped it by bringing an element that has only 3 valence electrons. This element is called boron. Now what is going to happen? Silicon is going to make its covalent bonding with the 3 valence electrons, but again 1 electron will be left, and this is known as a void, or this is now a positive element. That's why we are saying it is a p-type material. So now this hole is open. The electron of silicon, which is free, can easily come and join this hole. So again, this can become as a conduction element. Again, if this electron moves from here and fills this hole, a hole will be created over here. Similarly, another electron from another boron element, let's say if there is a boron over here, this electron will come and fill this hole, and this process keeps on continuing in this lattice structure. So but we have created a p-type semiconductor material. This is known as p-type. It has majority carriers which are positive, or we call them hole. Minority carriers are electrons, and thus we create a p-type material by an external influence, or what we call as doping. So again, to remember things, always electrons and holes are trying to fill each other. So if the electron is moving from one point to fill a hole over here, the same hole is now created over here, and we understand that the hole has now moved from this position and come over here. So this is known as the electronic or hole flow philosophy. Majority and minority carriers, obviously if we have more electrons, we say that it is majority carriers are electrons, and obviously in that material the minority carrier will be holes. Similarly, if we have a substrate or a material where we have a p-type, which means that the positive are in majority carriers and electrons are in minority. If we have an n-type material, it means that electrons are in majority and holes or normally positives are in minority. So these are the terms that we normally utilized for majority and minority carriers in p-type and n-type materials. Okay, so that's it for the first lecture on electronic devices and circuits, where we have talked about the atomic level. We have seen what is semiconductor material, what are the holes and electrons, how are the materials created, which materials are important when we are talking about electronics. 2 things to remember if I summarize. Electronics basically deals with the devices that are made from semiconductor materials. Second point, electronics deals with the control of flow of electrons to perform certain tasks. And all these lecture slides or today's lecture was all about that.